Hey everyone, welcome to today's Explainer. Today, we are unpacking a truly groundbreaking mathematical framework from the research of Kyle McLean Smith. It's a paper that completely rethinks how we measure, map, and frankly compare the very fabric of reality itself. Specifically, we're looking at how Smith solves a massive problem in math and physics. How do you escape infinite loops and scale-dependent metrics? Well, he does it by totally rethinking our coordinate systems. Now, I know that might sound complex right off the bat, but the absolute beauty of this research is that it rests on geometry you can actually visualize.
So let me ask you a question. How do you mathematically compare thermodynamic temperature to capital wealth distribution? Unless you're running a very strange hedge fund, it's a ridiculously difficult question to answer. We intuitively know comparing apples to oranges is tough, right? But what happens when you literally need to compare the physical heat coming off a computer chip to the economic distribution of wealth in a country? These variables are just vastly heterogeneous. If you try to graph them together, the numbers either simply don't talk to each other, or one completely overwhelms the other. It's basically the ultimate measurement dilemma.
Okay, let's dive into this. Here is our roadmap for today. First, the measurement dilemma. Second, the fractional shift solution. Third, bounded in the unit interval. Fourth, enter Thales' theorem. And finally, the continuous triangle manifold.
Starting with Section 1, the measurement dilemma.
In standard mathematics, metallic means, think of things like the golden ratio, are formulated as pure continued fractions, but there's a big catch here, and it's called standard integer indexing. These traditional formulations anchor the representation to a specific integer offset, usually called m, meaning the value is always mathematically unbounded. It's always going to be greater than or equal to 1. If you try to use this to map temperature and wealth, the scales just run away into infinity. It doesn't work. But Smith introduces something called fractional shift indexing. This acts as a universal metric with a strictly bounded limit, and that is what allows us to finally normalize all that heterogeneous data. Let's take a closer look at how that shift actually works.
Moving on to Section 2, the fractional shift solution.
Now, what's really interesting here is how elegant this solution actually is. Standard metallic means are typically written as a continued fraction index, basically m semicolon m m m. To fix the unbounded, infinite nature of this, Smith's framework applies a brilliant normalization transformation by literally just changing the leading integer term to a 0. That's it. So m semicolon m m m simply becomes 0 semicolon m m m. By tweaking just this one single number, we completely reshape our analytical capabilities.
Let's actually look under the hood at the algebra for a second. Taking the standard metallic mean, which again is anchored to that integer offset m, we apply our fractional shift. By changing that leading integer to 0, the algebraic value essentially becomes the reciprocal of the standard mean, so it's 1 over sigma sub m. Mathematically, this new fractional shift resolves to a very specific equation. It's the square root of m squared plus 4 minus m all divided by 2. And this specific algebraic tweak does something absolutely crucial to the resulting value.
Which brings us to Section 3, bounded in the unit interval.
So the crucial point of all that math is this specific interval, 0 to 1, and specifically exclusive of 0 and inclusive of 1. By applying that fractional shift we just talked about, we guarantee that the resulting number can literally never exceed 1. It acts like a mathematical safety valve. It entirely prevents these values from drifting out into infinity and breaking our models.
I want you to really think about the real-world utility of this. Because the fractional shift is strictly bounded within this unit interval, it provides a scale-invariant, dimensionless metric. What does that mean? It means we've completely removed the specific units of measurement. You literally don't have to worry about degrees Celsius or dollars anymore. This unit interval acts as a universal canvas. For the first time, totally different forces operating on completely different scales, like the thermodynamic heat in a tiny circuit board versus the massive flow of capital wealth in a global economy, can finally be mapped together accurately on a single comparative coordinate axis. It's a real game changer.
Section 4, enter Thales' theorem.
To actually build this universal canvas, the paper utilizes Thales' theorem. If you remember from geometry class, this is the principle stating that any point on a semicircular boundary forms a right triangle perfectly satisfying the Pythagorean condition, a squared plus b squared equals c squared. Now you might be wondering, how does this ancient geometric law from Greece bridge the gap to our newly bounded data? Well, it allows us to generalize discrete, rigid stepped math onto a smooth, continuous geometric space.
Let's walk through how Smith translates those dense equations into straightforward geometry. Step 1, we take the horizontal base of our right triangle, the infrastructure parameter, A, and normalize it to equal exactly 1. Next, we substitute A equals 1 into the invariant decay ratio, which is C minus B over A. Because A is 1, the denominator completely disappears. That's the beauty of it. So we derive a beautifully simplified decay parameter, D equals C minus B. Using our Pythagorean theorem, our final geometric parameter D simplifies all the way down to the square root of 1 plus B squared minus B.
And finally, section 5, the continuous triangle manifold.
And this right here brilliantly illustrates the real breakthrough of the paper. Look closely at the variable b. In our previous continued fractions, the index m was strictly an integer, right? It was discrete, it was stepped, like walking upstairs. But in this new geometric framework, the vertical parameter b, the vertical leg of our right triangle, is no longer restricted to integers at all. It's an element of the positive real numbers, so it forms a continuous right triangle spectrum. It no longer behaves like stairs, it behaves as a fluid, smooth continuum.
So how do we connect this fluid triangle back to our original metallic means? We take our continuous parameter b and simply set it equal to m divided by 2. When you substitute that back into our decay formula, something amazing happens. It seamlessly maps this continuous right triangle geometry directly back onto the metallic mean family. And crucially, it achieves this without skipping odd members in the sequence. It's literally generating every single consecutive metallic mean purely from continuous physical geometry.
To summarize directly from the source material, by applying Thales' theorem, any point along a semicircular boundary satisfies the Pythagorean condition, mapping the discrete continued fraction indices m onto a continuous geometric right triangle manifold. Today, we've seen how normalizing a single integer to 0 bounds our data, and how right triangle geometry creates a universal canvas for comparing entirely different facets of our universe. It leaves you wondering, though, if discrete numbers like wealth and temperature can be mathematically mapped onto a continuous triangle, what other hidden continuous manifolds might be governing our seemingly discrete reality? Thanks so much for exploring this explainer with me today.